I apologize in advance if my bedroom fan is audible during this video. My recording room exists in a place where I can either keep it cool or keep it quiet, but not both. And this has been a very, very hot summer. I'll do my best to cut it out during the editing process, but it may not be perfect. Thank you for your understanding. It should be unsurprising that, shortly after we began putting things in space, we began to realize the benefits of taking photos from there. Beginning with the advantages of seeing the Earth itself from such a high altitude, we quickly learned that the further advantage of not having the atmosphere in between us and the rest of the universe is a big one. Today, we're going to look at the history of space telescopes, spacecraft designed to peer deep into the universe in a multitude of spectrums and tell us more about the nature of that universe. But first, let's pay some bills. This video is brought to you by Manta, the premium provider of the most high-quality sleep masks available. Gone are the days of simple one-size-fits-all masks that don't provide proper coverage. Manta masks are fully customizable, with an adjustable headband and removable eye cups that can be positioned just right to fit the unique shape of your head. The cups perfectly hug your eyes to provide a true 100% blackout experience, letting in no light to disturb your rest. And don't go thinking there's just one kind. In addition to their standard mask, there's also a silk mask and my personal favorite, the Sound Sleep mask. I prefer to listen to some soft ASMR while I sleep, and the Sound Sleep mask's high-quality adjustable headphones deliver a clear and crisp sound directly to my ears to help lull me to dreamland. But wait, there's also accessories. Cool eye cups to soothe your eyes and sinuses, steam cups to relieve dryness, and aroma dots that deliver a subtle hint of pleasant scents to your environment. Made from only the highest quality materials, the masks are air permeable, so you'll still feel that gentle breeze from your nightstand fan. So head on over to mantasleep.com or .ca if you're in Canada like me, and use my code CAH to get 10% off your first purchase. That's mantasleep.com, or just use my link in the description and code CAH. Thank you, Manta, for sponsoring this video. So today, I'm going to change things up just a little bit. Instead of covering every space telescope one after another, we're going to look through eras of time, from the beginnings of space photography to telescopes that have yet to be launched, and the discoveries that came with them and will come with them. I won't be discussing each individual spacecraft, so if I missed one, it almost certainly wasn't an accident. I call these videos brief for two reasons. First, it's kind of a joke, and second, there truly is much more detail I could go into for virtually every subject, but I keep it short for brevity's sake. So, as always, I encourage you to do your own research and learn as much as you can about anything I might not have covered in this video. Another good thing to take note of is the many different spectral types of telescopes. We tend to think only of visible light cameras such as those used by Hubble. However, there are a lot more ways to observe the universe. Hubble itself also used ultraviolet imagery, but there's gamma-ray telescopes, X-ray, infrared, microwave, and radio, so we'll also need to take note of the different kinds of imagery, as well as when they were most prevalent and how they worked. Visible light photography of the Earth itself began almost immediately, first from V2 and Aerobee sounding rockets in the late 1940s. Able to resolve little more than the Earth's curvature and some cloud coverage, it wouldn't be until the early 1960s that reconnaissance satellites further refined the techniques, and thus the first space telescopes were technically born. The purpose was different, they were pointed at Earth rather than the cosmos, but the function was, in many ways, the same. Perhaps the most well-known early reconnaissance satellite was the KH-7 Gambit, launched 38 times between 1963 and 1967, with 30 returning usable imagery. Credited with producing the first high-resolution satellite photography of Earth, I consider the Gambit among the first space telescopes strictly based on how its optics system functioned. Of its three separate cameras, the single strip camera created images reflected by a steerable flat mirror which fed into a large stationary concave mirror about 1.12 to 1.21 meters in diameter. The light then passed through a Ross corrector, which is a lens assembly for correcting aberration, which is blurring or distortion caused by dispersion of light. The Gambit strip camera is a classic reflecting telescope, with the satellite's motion creating a continuous series of panoramic images along a ground track. These images, largely declassified in 2002, were incredibly detailed for the time. Here's an image of a Chinese missile center from 1967. But what might be the most interesting aspect of the Gambit's function was how the images were obtained. Given that the camera produced high-resolution imagery on wide-format film, the bandwidth available at the time simply wasn't enough to have them developed and transmitted back to Earth wirelessly. So instead, the physical film was returned to Earth undeveloped via a re-entry capsule, but not all the way to Earth. This was the height of Cold War paranoia, and there was fear that top-secret spy satellite images could be intercepted by foreign forces on the ground. They even had self-destruct mechanisms, including dissolvable plugs to make them sink into the ocean if they weren't recovered quickly enough. So instead of taking that risk, Gambit images descended via parachute, and then, somewhere between 8 and 15,000 feet in altitude, they were snatched straight out of the air by modified USAF aircraft, usually a C-130 Hercules, using grappling hooks and winch systems. Cold War paranoia used to make us just do things. Like many things, the first space telescopes to look away from the Earth belonged to the Soviet Union, though they weren't dedicated space telescopes, more automated laboratories to study high-energy particles and cosmic rays. Named Proton, they utilized the then-new UR-500 heavy-lift ICBM, which had been designed to carry nuclear payloads. The UR-500 would later be named the Proton, which is confusing, but that's less important. The relevant part of the Proton satellites, 4 of which were launched between 1965 and 1968, is that 2 of their experiments included a gamma-ray telescope and a scintillator telescope, and since this is the first real mention of either, let's explain how those work. Gamma rays are a type of electromagnetic radiation that carry more energy and have a shorter wavelength than any other kind of wave in the EM spectrum. As a result, they pass through matter more easily than any other form of radiation, including through mirrors and lenses. They can't be focused through a normal optics system, as they pass through without bouncing or bending. As a result, gamma-ray telescopes operate more as a particle detector, using converter layers of thin metals to turn the rays into electrons and positrons. These particles leave tracks as they fly through detector layers, usually strips of silicon, which record tiny electric signals when they pass through. A bottom layer stops the particles and measures how much energy they had, which allows scientists to determine their direction and map out detection events over time into a visible image. Scintillator telescopes are similar. High-energy particles enter a scintillator block or crystal, bouncing off electrons and creating thousands of tiny light photons. Mirrors or special coatings then bounce the light towards sensors, allowing the creation of a visible image. So, with all of that said, what did the 4 Proton satellites actually uncover? Not much. Results were published in Soviet journals and technical reports, including NASA translations of Grigoriev et al. Papers from the mid-1960s, but no revolutionary discoveries emerged beyond basic spectral measurements. The data contributed more to early understanding of the cosmic ray spectrum and set the stage for later experiments, but they themselves established little more than upper limits and background characterizations of spectral measurements. Sort of a proof of concept more than anything else. The first true dedicated space telescope was the Orbiting Astronomical Observatory, a series of 4 telescopes launched by NASA between 1966 and 1972. They were managed by NASA Chief of Astronomy Nancy Grace Roman. Remember that name for later. The first OAO, launched on an Atlas Agena in April of 1966, suffered a power failure before its instruments could be activated. Its solar panels were unable to deploy, resulting in a mission termination after only 3 days. In December of 1968, the second OAO was launched on an Atlas Centaur, going much more smoothly and thus becoming the first successful dedicated space telescope. OAO-2 contained 2 major instruments, the Smithsonian Astrophysical Observatory facing in one direction and the Wisconsin Experiment Package facing in the other. The former, also called Celescope, had 4 12-inch Schwarzschild telescopes which differentiate from Newtonian telescopes by using 2 mirrors, a concave primary mirror at the back and a smaller secondary mirror, also concave, in front of it. Light comes in, hits the primary mirror, bounces to the secondary mirror, then focuses at a point between the 2 mirrors. In the case of the Celescope, this point was a UVicon, an ultraviolet light detector, which converted the light into electrons, which were in turn converted to a readable voltage to create an image. On the other side, the Wisconsin Experiment Package contained 7 different telescopes for ultraviolet observations. One was a 16-inch nebular photometer designed to get a good look at, wait for it, nebulae, 4 4-inch stellar photometers, and 2 objective grading scanning spectrometers used for redundant spectral coverage. So, what did all of this equipment find out? Well, the primary aspect is, again, proof of concept, being an initial confirmation that a space telescope was a viable scientific instrument. 2 of the 4 OAO satellites operated successfully for 6 years, providing the first observations of many objects in the UV spectrum. The two that failed were not failures in function, but in faulty hardware for one and a bad launch for the other. Getting into the more nitty-gritty, OAO made several important observations about stars, supernovae, and comets. For stars, UV observations showed that hot, massive stars such as O and B types were actually hotter than contemporary models predicted, implying they evolve and burn faster than initially believed. Furthermore, it observed the 2175 O interstellar extinction bump. By the way, that's O, not the letter O, but the Swedish character, in this case standing for angstrom. Anyway, 2175 O is a strong increase in UV absorption or scattering, referred to in astronomy as extinction. Electromagnetic radiation, light, is absorbed, blocked, or scattered from our perspective, often by particularly dense interstellar clouds of dust. Here's an example in the form of what is called a dark nebula. It's not that the stars are missing, they're simply concealed behind layers of dense dust clouds. OAO2 also made significant observations of the Nova Serpentis, which appeared in the sky in 1970 and was discovered by Minoru Honda at an observatory in Japan. Significant for being the first nova discovered in the modern era, this was the first time such an event could be looked at in multiple wavelengths, allowing for close tracking of the expansion of the shell surrounding it for the first time in history. It also made note of the fact that, while a supernova gets visibly dimmer in the sky, its ultraviolet brightness actually increases as the ejected material heats up. This demonstrated that novae dimming is actually a redistribution of energy across multiple wavelengths. Last but not least was the comet observations. Two comets, Tago Sato Kosaka and Bennett, were found to have enormous clouds of hydrogen gas surrounding them, vastly larger than what was visible, and sometimes bigger than even the Sun. This provided confirmation of the theory that cometary nuclei consisted mostly of frozen water, which breaks down from solar radiation into hydrogen and oxygen, creating the massive clouds observed by OAO2. Another significant early NASA space telescope was Small Astronomy Satellite 2, or SAS-2, operating from 1972 to 1973. The second in a series of 3 astronomy satellites, SAS-2 was the only one equipped with a telescope, specifically a gamma-ray telescope. It featured an improved design from the one on OAO, using an outer shield made of plastic to block unwanted particles and thus preventing false signals. The gamma rays that penetrated the shield would hit thin tungsten plates, turning them into an electron and a positron. The particles would then pass through 32 layers of spark chambers, basically wire grids containing gases that would create tiny sparks of light to light the path of the particles. Magnetic cores recorded precisely where these sparks happened. 4 plastic scintillators, as well as radiation detectors, helped measure the energy and direction of the particles, confirming whether or not they were real gamma-ray events. This complex instrument gave scientists the first clear maps of gamma rays from our galaxy, including imaging of pulsars from the Crab and Vela nebulae, as well as some diffuse background radiation. The 1970s saw 2 attempts at crewed space telescopes, with one by the USSR and one by NASA. Salyut 1, the world's first space station, had a small ultraviolet telescope installed aboard it in 1971 called Orion 1. Mounted on the outside of the station near the docking adapter, it had an 11-inch mirror and used a star tracker to keep aligned with its target as the station moved in its orbital path. Orion 1 took the first ultraviolet spectrograms of bright stars like Vega and Beta Centauri, obtaining high levels of detail for the instruments at the time. A second telescope, Orion 2, was installed on Soyuz 13 in 1973, which was specifically modified to be an astronomy-focused mission. This was more of a survey-style instrument, using a wide-angle telescope with a 5-degree field of view to capture ultraviolet spectrograms of many stars at once across a large patch of sky. The NASA Crewed Space Telescope is one we've talked about a lot, Skylab. More specifically, the Apollo telescope mount that was a major part of Skylab. We've discussed Skylab at length in another video, but let's do a quick crash course of the ATM and how it came to be. One of the many projects of the late 1960s Apollo Applications program, the original concept was to mount the instrumentation on a deployable unit attached to the service module. Later, it was changed to be integrated into the ascent stage of an Apollo lunar module, operated remotely by an Apollo command and service module in orbit nearby. When Skylab was proposed as a wet workshop, the ATM was proposed to be attached to it in orbit, requiring 2 launches. Once Skylab had evolved into an expanded dry workshop, the ATM would be launched already attached. This would actually inadvertently save Skylab. Problems during launch destroyed one of the workshop's 2 solar arrays and prevented the other from deploying at first, requiring the first crew operations to rely entirely on the 4 smaller ATM solar arrays. The Apollo telescope mount used 8 major solar studies instruments. 2 X-ray telescopes, an extreme ultraviolet spectroheliograph, an ultraviolet spectrophotometer, an ultraviolet spectrograph, a visible light coronagraph, and 2 hydrogen alpha telescopes. If you couldn't tell from the terminology, the ATM was meant primarily to study the Sun. It observed numerous dark patches in the Sun's outer atmosphere where hot gases are thinner and cooler than their surroundings, observed clearly for the first time. Scientists learned that these dark patches are effectively leaks in the weaker points of the Sun's magnetic field, allowing solar wind streams to blow out into space. It also observed dramatic changes in the solar corona, including mass ejections, restructuring our thinking about the stability of the corona. Incredibly detailed and clear first-time looks at solar flares were observed in real time across multiple wavelengths, giving new details on how flares start and how their energy releases. By the mid-1970s, international efforts at space telescopes had begun. The European Space Agency ESA launched Celestial Observation Satellite B, or COS-B, hitching a ride aboard a NASA Delta II at Vandenberg Slick 6 in 1975. A gamma-ray telescope, it operated for 6.5 years until 1982, increasing the amount of data on gamma rays by a factor of 25 and adding the same number of entries into the Cambridge Catalogue of Radio Sources. Aryabhata, launched in 1975 aboard a Soviet rocket, was India's first satellite. It contained an X-ray astronomy telescope designed to study celestial X-ray sources, however, it only operated for 5 days before it experienced a power failure. Japan attempted a similar X-ray astronomy satellite, Corsa-A, in 1976, but it was lost due to the failure of its Mu-3 launch vehicle. A replacement, Corsa-B, was launched in 1979 and operated successfully for around half a decade. The 1970s into the early 1980s was the golden era of X-ray space telescopes. NASA delivered a battery of 3 between 1977 and 1979, High Energy Astronomy Observatory 1 through 3, with the second one being named the Einstein Observatory. The first was able to provide nearly constant monitoring of X-ray sources near the ecliptic poles for nearly 2 years, as well as do detailed studies of a number of objects for periods of up to 3 to 6 hours. The second discovered approximately 5,000 sources of X-ray emission during its 3 years of operation and was the first X-ray experiment able to resolve an actual image of the observed sources. It was also able to confirm one of 2 theories regarding the background X-ray radiation across the sky. This radiation has a certain uniformity to it, indicating that it likely originated from outside the Milky Way. The 2 dominant explanations for this have been that 1. A hot gas spread uniformly throughout space, or 2. Numerous distant point sources such as quasars appear to blend together due to their distance. The Einstein Observatory confirmed that a large portion of X-ray background came from those distant point sources, lending more credence to the second theory, which would later be confirmed and refined by later experiments. Japan launched Tenma, no not that Tenma, it just means Pegasus, in 1983, an X-ray telescope intended to be a successor to the Corsa missions. Despite boasting superior temporal and spectral sensitivity, a battery failure in its second year severely limited its operations, and its X-ray observations were stopped in the next year, though it did continue to operate its other instruments for a total of nearly 6 years. Most of its discoveries would be related to its other instruments, so unfortunately there isn't much else to say about it in this specific video. I mostly just wanted to invoke Tenma's name and potential wrath. The USSR launched Astron, the largest ultraviolet telescope ever at the time, in the same year as Tenma aboard a Proton K. Boasting both an 80cm UV telescope and an X-ray spectroscope, it performed its best work in 1985 and 1987. First, it made observations of Halley's Comet as it passed through the solar system, allowing for detailed analysis of the comet's coma, which is the large nebulous envelope of gases that surround it. In 1987, a Type II supernova was observed in the Large Magellanic Cloud, the closest observed since 1604. Astron and similar observations of the supernova would result into much insight in how a massive star's core collapses into a supernova. It provided the first direct observations of the energy created by its visible light emissions, proving that the long-duration explosive cloud was in fact highly radioactive in nature. Again in 1983, ESA launched EXOSAT, hitching a ride aboard a NASA Delta III. It would operate for 3 years, making around 1,780 X-ray observations of everything from galactic nuclei, stellar coronae, white dwarfs, galaxy clusters, and supernova remnants. Operating in a highly elliptical orbit that took it out roughly halfway to the Moon and then back into low Earth orbit, it located X-ray sources using the lunar occultation technique. Basically, it uses the moon passing in front of the X-ray source to measure the drop in X-ray count rates and rise again once the object appears on the other side of the moon. This allows it to precisely triangulate the object's position by effectively using the moon as a ruler. From the late 1980s onward, visible light telescopes began to enter the scene. Let's talk about the big one first. Originally named the Large Orbiting Telescope, with planning dating back all the way to before the first moon landing, the Hubble Space Telescope was something of a monolith as far as space telescopes go. Astronomer Lyman Spitzer spent much of his career pushing for development of a space telescope. All the way back in 1946, he wrote a paper on the advantages of one, pointing out that its angular resolution wouldn't be limited by the distortion caused by the atmosphere, and that ultraviolet and infrared astronomy are also largely impossible from within the atmosphere. By 1962, the US National Academy of Science recommended development of a space telescope to NASA, and 3 years later, Spitzer was appointed head of a committee in charge of exactly that. Once the first NASA space telescopes had proven the concept, NASA began firm plans for a large telescope with a 3-meter mirror in 1968, the Large Orbiting Telescope or Large Space Telescope. They were hoping for a launch by 1979. The journey was difficult. The plans focused on being able to do crude maintenance to extend the telescope's working lifetime, aligning the concurrent development of the space shuttle that would allow such a thing to be possible. As NASA began to experience its diminished post-Apollo budget, Associate Administrator for Space Science Noel Hinners made a bold move. After NASA Administrator James Fletcher proposed $5 million for a placeholder Hubble budget, Hinners subsequently cut the funding entirely. He said later, quote, "I figured in my own little head that to get that community energized, we'd be better off zeroing it out. Then they would say, whoa, we're in deep trouble, and it would marshal the troops. So I advocated that we not put anything in. I don't remember any of the detailed discussions or whether there were any, but Jim went along with that, so we zeroed it out. It had, from my perspective, the desired impact of stimulating the astronomy community to renew their efforts on the lobbying front. While I like to think in hindsight it was a brilliant political move, I'm not sure I thought it through all that well. It was something that was spur of the moment." The plan worked. Hubble's cut triggered a nationwide astronomer lobbying effort, with several of them meeting with congressmen and senators, as well as performing large-scale letter-writing campaigns. Eventually, this would result in the Senate allocating half of the original congressional budget. This would reduce the scope of the project, planning for a smaller mirror and for collaboration with ESA to provide funding and supplies. In 1978, Congress approved a $36 million budget, at which point work began in earnest, now aiming for a 1983 launch date. In that year, instead of launching, it would receive its proper name after Edwin Hubble, the astronomer who confirmed the expansion of the universe and essentially validated the Big Bang Theory. Having begun in 1979, Hubble's construction was divided among many places. The Marshall Space Flight Center was responsible for the design and construction of the telescope itself, while the Goddard Flight Center controlled scientific instruments and ground control. Perkins-Elmer designed the optical assembly and fine guidance sensors. Lockheed constructed and integrated the telescope into the spacecraft that housed it, which may look familiar. The design heritage of the spacecraft itself can be traced back to the KH-11 spy satellite, though it isn't clear exactly how direct this cousinhood is. Much of the KH-11's exact details continue to be classified even today, so all we can say for sure is that Lockheed's spacecraft design was definitely inspired by their previous work in spy satellites. This spacecraft design was a major feat of engineering. Hubble would need to withstand intense sunlight, long periods of shadow, and the quick transition between the two. At the same time, it would need to be extremely stable, allowing for it to be pointed with precision accuracy at its targets. Multiple layers of insulation kept it within a stable temperature range, all around a light aluminum shell. Within that shell, the working parts of the telescope are kept aligned with a graphite epoxy frame, which require a nitrogen purge before launch to reduce the risk of water particles forming into ice on the instruments once they're in space. To ensure accuracy and reliable positioning, Hubble uses a pointing control system composed of 5 different types of sensors: magnetic, optical, and 6 gyroscopes, as well as 2 types of actuators, magnetic torquers, and reaction wheels. Its initial computer systems were 2 1.25 MHz DF224 computers built by Rockwell Autonetics specifically for use in spacecraft. Designed with double and some triple redundant components, these computers would slowly be upgraded and eventually replaced during servicing missions. In terms of scientific instruments, at least at first, Hubble carried 5: the Wide Field and Planetary Camera, the Goddard High Resolution Spectrograph, the high-speed photometer, the faint object camera, and the faint object spectrograph. The Wide Field and Planetary Camera, likely the most well-known instrument, was built in NASA's Jet Propulsion Lab and has 48 separate optical filters to focus on different spectral lines. The Goddard High-Resolution Spectrograph was built by its namesake, the Goddard Space Flight Center, and was optimized for ultraviolet work. The Faint Object Camera was built by ESA, and the Faint Object Spectrograph by the University of California, San Diego, and Martin Marietta. Lastly, the high-speed photometer was designed and built at the University of Wisconsin-Madison and was made for both ultraviolet and visible light observation of stars that vary in their brightness over time. Hubble is a Cassegrain reflector. It uses two mirrors to collect and focus light, giving a long focal length in a short, compact tube. The only disadvantage is that these mirrors are difficult to fabricate and test. We can see here Hubble's primary mirror being ground into shape at Perkins-Elmer in 1979. Little does this man in this image know, the mirror would end with a serious flaw. The outer perimeter would wind up being too flat by about 2200 nanometers, which is about 1/11,000th of an inch. Smaller by a pretty big margin than a single human hair. Hubble was ready, albeit late and extremely over budget, by the time of 1986. However, the Space Shuttle fleet was grounded and the launch postponed for several years following the tragic loss of Shuttle Challenger. The delay kept Hubble in a clean room, powered and ready to go, costing around $6 million per month and further driving up overall project costs. Engineers did take the time to perform tests and prepare the yet incomplete ground control software, and then finally, on April 24, 1990, Hubble finally launched aboard Shuttle Discovery.
And liftoff of the Space Shuttle Discovery with the Hubble Space Telescope, our window on the universe.
Mission Control, Houston.
The flight was entirely successful, the telescope released from Discovery's payload bay using its robotic arm, but a problem quickly was realized that turned NASA's most expensive science mission of all time into a temporarily embarrassing boondoggle. A few weeks after its launch, Hubble began to return some concerning images. While the overall quality was way better than that of a ground telescope, it fell far below what had been expected of the project. Images focused on a singular point came out far more spread out, about 10 times further than they should have been, indicating the primary mirror had been polished to the wrong shape. Very, very slightly, as discussed. This was causing spherical aberration. Light reflecting off the edge of the mirrors focuses on a different point from the light reflecting off the center. This was less of a problem with high-resolution images of bright or relatively close objects, such as local planets, but it would cause nearly all cosmological programs that focused on distant, faint objects to be entirely cancelled. NASA went through the ringer with scientists balking at the cost of what was essentially a broken telescope, and politicians to begin to carefully scrutinize the overall competence of the space program. Rather famously, in the film Naked Gun 2.5, Hubble is featured on the wall of a restaurant with images of other famous disasters sandwiched between the failed Ford cars of the future and the 1960 San Francisco earthquake. Fearing total project abandonment, NASA's Astrophysics Division worked desperately on a solution with an allocated $60 million repair budget. The first servicing mission had already been scheduled for 1993, and Charles Pellerin, director of the Astrophysics Division, committed to fixing Hubble by the next year. A backup mirror had been ground, but it was simply infeasible to replace the entire mirror in orbit, or to return the entire telescope to the ground for a refit. Instead, a solution was implemented that worked on a similar principle to spectacles for eyesight. Since the mirror had been ground to the wrong shape in such a specific way, a new set of optical components were designed that had the exact same flaw, but on the opposite side. The plan was to put glasses on the telescope. The Corrective Optics Space Telescope Axial Replacement, or COSTAR, was constructed using two mirrors in the light path with one intentionally flawed to correct the aberration. It came at a high price. To be fitted onto the telescope, an existing instrument was forced to be removed, and astronomers chose the high-speed photometer as their sacrifice. COSTAR was installed in December of 1993, successfully over a period of 11 days. Hubble would, by 2009, see a total of 4 servicing missions, replacing solar arrays, aging gyroscopes, and eventually all of the instruments that had required COSTAR. COSTAR itself would then be returned to Earth, now displayed at the National Air and Space Museum in Washington, D.C. So, having been in operation for the last 26 years, what has Hubble achieved? While it is fast approaching the end of its life, Hubble has carried out several projects, both on its own and in collaboration with other spacecraft. Perhaps its most well-known project is the Deep Field images, the most well-known of which was taken in 1995. The premise behind these images is simple. Point the telescope at a very small section of the sky, about 2.6 arc-minutes across, which is roughly equivalent to a dime viewed from a distance of about 46 feet away. Only a few foreground stars in the Milky Way are within the images. They're otherwise largely empty, at least at a glance. However, after taking over 300 exposures over the course of multiple days, thousands of distant galaxies were revealed, each holding hundreds of billions of stars and hundreds of billions of planets. By analyzing the redshift values, which is basically how we determine cosmological distance, it further cemented our understanding of how the universe is continuing to expand. Further major projects include the Cluster Lensing and Supernova Survey, which observed 25 galaxy clusters to examine how dark matter was distributed throughout them. There was also a photomosaic of the Andromeda Galaxy, combining 411 individual exposures taken between 2010 and 2013, stitched together into a 1.5 billion pixel image. It shows the northern side of Andromeda's galactic disk in visible light, showing a distance of approximately 61,000 light-years across. It contains over 200 million astronomical objects and has mapped a massive portion of our neighbor galaxy. It's also worth noting that the relatively lossy JPEG file I saved for this video is 290 megabytes, which is massive for a singular photo. My editing software is not particularly fond of this. In addition, Hubble has captured some of the most visually stunning images of planets, various nebulae, and other distant galaxies, many of which are famous enough for anyone to recognize even at a glance. Let's just take a moment to appreciate some of those now. Of course, Hubble was not the only visible light telescope of its era. In fact, the year before it launched, ESA launched Hipparcos aboard an Ariane 4, dedicated to precision astronomy and parallax measurement. Its 4-year mission would result in the Hipparcos Catalog, a high-precision catalog of over 118,000 stars, published in 1997. Hubble was, in fact, the first of NASA's Great Observatories program, which launched a battery of 4 large, powerful telescopes between 1990 and 2003. In the year following Hubble's launch, the Compton Gamma Ray Observatory was launched by Shuttle Atlantis on STS-37, operating for 9 years until it was deorbited in June of 2000. It conducted full sky surveys to detect bursts of gamma rays, discovering 2,700 detections over the course of its life. The majority of these came from outside the Milky Way, indicating an enormous amount of energy to so easily reach man-made instruments. During this time, there was also an increase in infrared telescopes, beginning with the Infrared Astronomical Satellite, or IRAS, a joint project between NASA, the Netherlands, and the United Kingdom. The first telescope to be dedicated to an infrared survey of the entire night sky, IRAS was launched in 1983 and operated for 10 months. It observed 250,000 infrared sources at different wavelengths, and its success would lead to the Infrared Telescope mission of the Space Shuttle on STS-51F, which would in turn spur on the development of the Spitzer Space Telescope, which we'll come back to. An interesting thing to note about infrared satellites is that their lifetimes are limited by design. To work effectively in their required ranges, IR telescopes need to be kept at cryogenic temperatures, around -200 degrees Celsius. Most would achieve this through evaporation of superfluid helium, and once all of that was gone, the telescope would heat up to a point where it no longer functioned. Such was the case for the Infrared Space Observatory, a joint ESA, JAXA, and NASA operation launched on an Ariane 4 in 1995. It was designed to study infrared light at specific wavelengths and operated for a remarkable 28 months and 22 days. The ISO served as a kind of follow-up to IRAS, using the infrared sky map created by IRAS to provide more detailed observations of around 30,000 specific sources. It was able to perform around 45 observations a day, and throughout its lifetime managed 26,000 of its designated 30,000 targets. It found some interesting results that included planet formation around old dying stars, hydrogen fluoride gas within interstellar clouds, water vapor in star-forming regions, and more. In 1999, NASA launched WIRE, or Wide Field Infrared Explorer, intending to perform a 4-month infrared survey. However, a few hours into its mission, the telescope dust cover prematurely ejected and exposed the lens to the Earth. The bright light of the Earth caused a higher than usual heat load, too much for the cryogenic cooling to handle. The system designed to boil off the helium began to vent gases at rates far higher than expected, which acted like a thruster that caused the spacecraft to spin. Unable to correct this, the spin accelerated to around 60 RPM by the time all of the helium was expended, and the telescope was officially non-functional. In the same year as WIRE, NASA launched the third great observatory and the physically largest payload ever to be launched by the space shuttle, the Chandra X-ray Observatory. Requiring the specific use of Shuttle Columbia due to its extra space from the lack of an external airlock, Chandra is sensitive to X-ray sources 100 times fainter than any previous telescope due to the high angular resolution of its mirrors. Given that previous telescopes used more of an X-ray detector rather than a full telescope, let's take a moment to discuss how Chandra actually works. It uses a Wolter telescope, which is able to reflect X-rays if they graze a smooth surface at a very shallow angle, sort of like skipping a stone on the water. 4 hyperboloid mirrors and 4 paraboloid mirrors are nested together, allowing for a much sharper focal point that the X-rays converge to, hitting a detector that records the final image. Over the course of its life, Chandra has provided the first clear X-ray images of various supernovae, evidence of supermassive black holes across the universe creating a mysterious X-ray glow across the sky, and jets of hot material ejecting from the center of several black holes. It also provided further evidence of dark matter. In the Bullet Cluster, which is a pair of colliding galaxy clusters, Chandra showed that hot gas was slowing down during the crash, but invisible matter appeared to be passing straight through. Chandra's mission is still ongoing, having more than a decade of operational lifetime left. However, in 2024, it faced the threat of early cancellation due to a decrease in congressional funding. Astronomers began a public outreach project to persuade Congress to keep Chandra within its budget, but as of right now, the telescope's future remains very much up in the air. So far up you could say it's in space.
Oh, brother, this guy stinks!
The Spitzer Space Telescope, launched in 2003, is the 4th great observatory and remains the longest-lasting infrared telescope mission, operating until 2009 when its liquid helium was depleted, though it continued non-IR observations until 2020. Spitzer utilized several new methods to allow its 6-year IR mission, including an Earth-trailing solar orbit that kept it away from the radiated heat of the Earth. It would initially follow the Earth but at a slower orbital speed, falling just a little further behind it each year. It also utilized a sun shield in the form of its solar array, positioned in a way that protected the telescope assembly from the blistering heat of the sun, while the opposite side was painted black to further reduce heat. Over the course of its life, participating institutions as well as astronomers around the world were able to submit proposals for observations with the telescope. It was the first spacecraft to capture light from planets outside of our own solar system, whereas we're normally only able to see the silhouettes of these planets as they pass in front of their parent stars. It also helped find the TRAPPIST-1 system, discovering 7 rocky planets around the parent star, the most ever seen around a single star. In 2009, scientists used Spitzer data to create the first weather map of an exoplanet, charting temperature variations and even roaring winds whipping through the atmosphere of gas giant HD 189733b, Ketchy, approximately 64 light-years away. In the same year, Spitzer was turned on Saturn, discovering a giant faint dust ring that is invisible in normal light, named the Phoebe Ring. GALEX, or Galaxy Evolution Explorer, was launched by NASA in 2003 to observe star formation in ultraviolet. Air-launched on the Virgin Galactic Pegasus rocket, GALEX had a primary mission of 29 months, after which its operations were extended until 2013. It would create the first UV sky map, taking photos of millions of galaxies and stars invisible to the naked eye, providing a new look at hot young stars and star-forming areas. I don't like the sound of hot young stars. Anyway, very faint disks and arms of stellar nebulae previously unknown were also uncovered by GALEX, as well as existing regions being realized to be much, much larger than initially believed. The Neil Gehrels Swift Observatory, launched in 2004 aboard a Delta II, was developed as a partnership between the Goddard Space Flight Center and an international consortium that included the US, the UK, and Italy. Its primary purpose was to study bursts of gamma rays as well as the afterglow in both the X-ray and UV spectrums. With a sensitivity far greater than the Compton Gamma Ray Observatory, Swift detects around 100 gamma ray bursts a year and continues to operate to this day. It was briefly at risk of dragging down into Earth's atmosphere, but a mission to raise it was launched just days ago at the time of writing this on July 3rd. However, that mission is going to take several months while it checks out its own systems and then performs a detailed analysis of Swift before performing the reboost. All we can say for now is that the reboost mission was launched successfully aboard the Virgin Galactic Pegasus rocket, and contact was made with the spacecraft after it reached orbit. Suzaku, named after the mythical vermilion bird of the south, was launched by JAXA aboard the MV rocket in 2005, and I'd just like to point out that its X-ray telescope unit looks like an air filter I would install in an old Corvette. It actually contained 4 instruments for high spectroscopic resolution. In addition to its X-ray telescope, it had a hard X-ray detector and 2 X-ray imaging spectrometers. Its primary achievement was the discovery of what was referred to as fossil light from a supernova remnant. IC443, also known as the Jellyfish Nebula some 5,000 light-years from the Earth, was found to contain X-rays from fully ionized silicon and sulfur. This is significant because it provides the first robust evidence of recombining plasma in a supernova remnant and acts as a fossil record of the immediate post-explosion phase. Supernovas tend to cool very quickly after their initial explosion, and these ionized particles are essentially trapped in the early stage of that explosion. Agile, a satellite operated by the ISA, the Italian space agency, was launched in 2007. I'm not going to try and pronounce its full name because I find the Italian language too funny to speak in a serious tone. Agile was both an X-ray and gamma ray observatory, using incredibly light materials with its instruments weighing only 100 kilograms. Planned to operate for only 3 years, it kept going for almost 17 years, deorbiting in 2024 after studying galactic nuclei, gamma ray bursts, X-ray sources, non-identified gamma sources, and more. It made several noteworthy discoveries, including variable emissions from the Crab Nebula. This is significant because the Crab Nebula was previously believed to be a rather steady and reliable candle in the night sky, but in fact has frequent flare-ups of high gamma ray activity. It also provided evidence that supernova remnants tend to speed up cosmic rays, pushing them out further into the universe around them. Strong gamma ray bursts from black holes helped further understanding of how black holes launch matter, which sometimes occurs very near to the speed of light. Overall, it could be said that Agile was a small and smartly built satellite that punched well above its weight. NASA launched the Kepler Space Telescope to study Earth-sized exoplanets in 2009. Part of a program that focused on lower-cost science missions using a simple optical telescope design and having the singular scientific instrument of a photometer, it continuously monitored the brightness of about 150,000 stars in its field of view. It then transmitted this data back to Earth, and the data would then be analyzed. When a star showed periodic dimming, this showed that once other options were eliminated, a planet orbiting the star had passed between the star and the telescope during its orbit. Over the course of Kepler's 9.5-year lifetime, it observed around 500,000 stars, detecting 2,778 confirmed planets. After 2 of the spacecraft's reaction wheels failed, the K2 Second Light proposal was given, a modified mission that would rely on being able to use only the 2 remaining reaction wheels and its thrusters and focused on planet detection around smaller, dimmer red dwarf stars. By 2018, the spacecraft ran out of fuel and it was shut down before a new spacecraft would continue its mission in the same year. TESS, standing for Transiting Exoplanet Survey Satellite, is able to search for exoplanets in an area 400 times larger than Kepler, using the same method of observing planetary transits across the host stars. Its mission is still ongoing, 8 years in, but has, as of now, confirmed 885 more exoplanets out of nearly 8,000 candidates. Targeting a wider field for shorter durations allows TESS to focus more on what are called hot Jupiters, gas giants with relatively close and therefore fast orbits around their parent star. Longer period planets are harder to detect, as TESS may only observe a single pass as it focuses on that area, which is ambiguous and requires further observation to confirm. It's focused more on confirming previously identified candidates, refining Kepler's work rather than simply picking up where it left off. JAXA launched Hitomi in 2016, and while it failed too soon to do any significant work, I want to mention it primarily for its name. JAXA has a tendency to have some really cool names for their spacecraft, such as the Akatsuki Venus spacecraft meaning dawn, or Hayabusa named after the Peregrine Falcon, and Hitomi is no exception. Thing Japan indeed. An X-ray satellite meant for studying the universe's more energetic processes, Hitomi refers to the pupil of an eye, the entrance window or aperture of our optical biological components. At the same time, it refers to a legend of a painting of 4 dragons. The legend describes a painter who was on a street painting 4 white dragons. None of them had pupils in them, and the painter was asked, "Why don't you paint Hitomi? It is not complete." The painter, after some humming and hawing, drew Hitomi on 2 of the 4 dragons, which proceeded to come to life and fly away, while the other 2 remained still. The idea behind the story is that Hitomi, this window to the soul, is the one last but most important part, and the spacecraft was given the name as the final part of the Astro series of satellites. Unfortunately, after 37 days in orbit, Hitomi had an incident with its control system which put it into an uncontrolled fast spin. Its components that were less robust broke apart, putting the spacecraft into 5 pieces, and contact was officially lost 37 days and 16 hours after its launch. A number of satellites have been launched in recent years that have yet to complete or publish any significant work, making me want to refrain from talking about them until a later date. For instance, the Imaging X-ray Polarimetry Explorer from NASA, the X-ray Imaging and Spectroscopy mission from both NASA and JAXA, the Interface Region Imaging Spectrograph from NASA, all launched within the last half-decade, but their work is complex and spread over many years. Their stories are far too incomplete to be told here, but at the very least I've given you their names. I encourage you to use the Google machine before we move on to these final projects. We come now to the big boy, the single largest telescope in space, one of the most unique and complicated, and the one that had the entire space community puckering for the 8.5 minutes it spent aboard the Ariane 5 rocket that took it to orbit, the James Webb Space Telescope. Now, you may look at this thing and think, that doesn't look like a telescope. And you'd be right. By a traditional standard, it looks like some kind of science fiction orbital laser cannon. The optics of Webb are truly something else. Its primary mirror is 21 feet wide, made of 18 hexagonal segments of lightweight beryllium, which is resistant to heat expansion. These tiles are coated with a thin layer of gold to help them reflect infrared light. A secondary mirror for bouncing the light back toward the center sits on a tripod structure at the front. A tertiary mirror cleans up aberrations, and a fine steering mirror makes tiny adjustments for fine-tuned, extra-stable pointing. The primary mirror was folded up to fit inside the rocket fairing, and once it made it to orbit, had to use 178 release mechanisms to perform over 50 major deployments, configuring itself into a usable state. It was this process, with over 300 possible points of failure, that would leave the entire telescope completely unusable and way too far away to repair, that had everybody so nervous. Before we go through that deployment process, let's talk about development to add some context to this high-stakes situation. A successor to Hubble had been talked about before Hubble itself even launched, but serious planning would take another decade. In 1994, after Hubble's flawed optics had been corrected, the HST and Beyond Committee was formed to study, quote, possible missions and programs for optical ultraviolet astronomy in space for the first decades of the 21st century. Hubble's success led to the committee's report on the concept of a much larger, colder telescope that was sensitive to infrared light, allowing it to look further back in time at distant galaxies. Hubble's own optical system, designed as what's called a warm telescope, effectively blinded it from IR emissions, so its successor would need a completely different design, with the initial report calling for radiative cooling below freezing. This is the reason James Webb sits out at the Sun-Earth L2 Lagrange point, varying between 250,000 kilometers and 832,000 kilometers away from the Earth. What was then referred to as the Next Generation Space Telescope took recommendations over the next decade, identifying research priorities and developing the program. NASA Administrator Dan Goldin coined the term faster, better, cheaper for future spacecraft, which would quickly become ironic, but did also involve opting for the segmented optics that would allow for a much larger mirror. In the mid-1990s, the projected cost of the NGST was around $500 million US. Goddard Space Flight Center, Ball Aerospace, TRW, and Lockheed Martin were hired to conduct technical requirement and preliminary concept studies. Launch was slated for 2007. By 2002, the project had been given the name of NASA's second administrator, James E. Webb, who had led the agency during much of the Apollo program. By the mid-2000s, further development and replanning had ballooned the budget out to $4.5 billion US, as well as approximately $1 billion for its 10 years of operations. By the late 2000s, its design had been finalized and begun to be constructed and tested. By 2011, Webb was in the final design and construction phase, and assembly was completed in 2016, marking the beginning of a rigorous testing procedure. A torn sunshield during a practice deployment further delayed the project, but by 2019, it was finally ready and was shipped to French Guiana for launch in 2021. Its budget now sat at $9.7 billion US. After an integration incident that was a little concerning, a clamp band release that caused vibrations to the telescope, though no actual damage was done, JWST was fueled with hydrazine and dinitrogen tetroxide before being encapsulated within the fairing in December of 2021. Then, finally, on Christmas Day, James Webb took off on a completely flawless launch into a transfer orbit. 27 minutes after liftoff, the telescope was separated from the upper stage, the last time the telescope was seen by any camera, and began its deployment sequence. First, its solar array was deployed, then its high-gain antenna. On day 3, the pallets that hold the sunshield were unfolded, then the deployable tower assembly on which the optical telescope element is mounted. On day 5, a momentum flap was deployed, which keeps the telescope's orientation while being buffeted by solar pressure, followed by the sunshield cover. The next day, a pair of mid-booms were deployed, which pull the center portions of the sunshield into place, then the sunshield membranes would separate into layers and tighten into their deployed positions. The secondary mirror's support truss was locked into place, then the aft radiator, then the primary mirror wings finally unfolded. After nearly a month, the telescope was finally fully deployed, and a trajectory correction burn was made to place it into its final orbit. And keep in mind, if any single one of these steps had failed, over 30 years of work and nearly $10 billion would have all been for nothing. It took a full 10 days for the telescope to simply begin to fully align its mirrors, using 132 actuator motors to carefully position them in increments of only 10 nanometers, about 1/5000th the width of a human hair. The process was described by NASA thusly, quote, "If the Webb primary mirror were the size of the United States, each mirror segment would be the size of Texas, and the team would need to line the height of those Texas-sized segments up with each other to an accuracy of about 1.5 inches. Anything but metric. The full alignment took nearly 3 months, taking images of distant stars to determine where in the night sky each segment of the mirror was pointing. Webb released its first full-color images in July of 2022, the first being Webb's first deep field image. Fun fact, if you see a deep field style telescope image, you can usually determine whether it was Hubble or Webb by counting the points on the stars. Webb's unique mirror format creates 6 pointed diffraction spikes, while Hubble only makes 4. While JWST's scientific findings are far from finished and will likely learn a lot more over the course of the next decade or two, there is already a decent amount to talk about after only a few years of operation. It has been widely believed that the earliest galaxies in the universe formed relatively slowly. However, JWST has found bright, well-formed galaxies that are a little under 300 million years older than the Big Bang, a cosmic blink on a long enough timeline. In the same vein, early black holes were discovered to be from only about 1 billion years after the Big Bang. This is significant because it makes it likely that they didn't form from early stellar collapses, but instead from collapsing gas clouds that were forming before the first stars even existed. JWST has also been able to study the atmospheres of exoplanets using the starlight that passes through them. Water vapor, carbon dioxide, methane, and sulfur dioxide have all been found in gas giant atmospheres, snow made of tiny silica flakes in the skies of one hot planet, and even hints of weather patterns such as morning clouds that are gone by later in the planet's day-night cycle. Again, JWST discoveries are likely to only increase over time, but for now, those are some of the most significant discoveries that it's made in only 4 years. Remember that new discoveries were made in 2024 using data from the Magellan probe, which launched in 1990. Just a few recent entries left now. Euclid, developed by ESA, was launched from Cape Canaveral in 2023, a wide-angle telescope with a 600 megapixel camera that is also intended to determine galactic redshift values. Using the phenomenon of gravitational lensing, which is how large masses in space visually distort objects near them from an observer point of view, Euclid intends to measure galactic redshift by a factor of 2, which is roughly equivalent to looking 10 billion years into the past. However, it is far from finished performing this mission as of right now. NASA launched SphereX, or Spectrophotometer for the History of the Universe, Epoch of Reionization, and ICE's Explorer, goddamn, in 2025. Despite the lengthy name, there isn't too much to say about it as, like Euclid, it's quite new. It's performing a near-infrared all-sky survey to measure the infrared spectra of around 500 million different galaxies. It will then classify these galaxies according to their redshift values in an attempt to refine our understanding of what forces were behind the inflation of the early universe. Also, it's cool because it looks like a big megaphone. So, what does the future hold for space telescopes? Well, quite a bit. China is expected to enter the space astronomy ring sometime later this year with Zhunchen, which operates similarly to Hubble with a docking port that allows for servicing missions, but with a much larger field of view. ESA will be launching Plato, an exoplanet detecting mission, in 2027. There are a handful of others, but the most worth mentioning, especially right now, is the Nancy Grace Roman Telescope. Named after the previously mentioned former NASA Chief of Astronomy, Roman is a powerhouse on a budget. Operating primarily with a wide field of view mirror donated by the National Reconnaissance Office, it uses two instruments, a wide field instrument and a 300 megapixel near-infrared camera. Roman will be able to provide images roughly comparable to Hubble in quality, but at approximately 10 times the size. It existed as concept studies around 2011 to 2012, and when the possibility of making use of a surplus NRO mirror became real, work began in earnest in 2018. In 2025, during the government shutdown, NASA clarified that certain missions, including Roman, would not be affected by their consolidation of buildings and equipment. It's currently slated for launch on August 30th, 2026, and I want you to listen very carefully to what I'm about to say. It's very likely that this is the first and only time I will ever say these words in my entire YouTube career. The Nancy Grace Roman Telescope is both ahead of schedule and under budget. While that budget is still approximately $4.3 billion US, that is about $300 million less than originally intended. I was a little worried when I started this video that it wouldn't be very interesting. However, what I ended up finding the most interesting is the different ways human beings have devised to make images out of the invisible. Particle detection methods to see what we cannot see, but know is there. Using shadows to detect planets that are hundreds of trillions of kilometers away. Turning radiation into electrons and shoving them into a metal grid so that we can perceive them. Even the primitive method of spy satellites taking photos on film and then flinging that film at the planet only for it to be snatched out of the air by a plane is incredible. I hope this subject was at least somewhat interesting for you too, and always remember, there is always more to learn.